Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we talked about type of semiconductor, that is basically we categorize semiconductor into two categories. One is intrinsic semiconductor, that is pure semiconductor, another is extrinsic semiconductor. And we understood what is exactly intrinsic semiconductor, how intrinsic semiconductors basically conduct current. We talked about the conductivity of intrinsic semiconductor, like what exactly at low temperature or very low temperature and 0 Kelvin semiconductor, intrinsic semiconductor, they are perfectly insulated, but when like temperature rises or it up to room temperature, then they start conducting, their conductivity increases. We understood also like why all this happen and how this happen, and we saw that actually if we look for the some practical applications of semiconductor, then intrinsic semiconductor, they have some conductivity, but the conductivity is not like sufficient for like devising, for designing some device, for making it useful. So we need to do something actually, and then we like did, that is doping, means we added some impurities, and that can be like added. So normally it's like 14 group element, we can add it from 13 group or 15 group, or we can say it's tetravalent semiconductors, silicon and germanium, they are tetravalent. We can either like a trivalent or pentavalent impurities. So depending on if we are adding a trivalent impurities, then additional holes are created in the semiconductor, and we call this as acceptor impurity because it can accept one electron, and this type of semiconductor we define p-type semiconductor. Similarly, in pure intrinsic semiconductor, if we are adding an n-type, means pentavalent impurities, then one excess electron will stay there, and that can jump easily into the conduction band, and that way it increases the conductivity of extrinsic semiconductor. And here we define the impurity added, we call that donor impurity, and the semiconductor thus formed is termed as like n-type semiconductor. So this is all we studied up to last class. We saw the relation of like density or charge carrier, like in there are holes and electron charge carrier in both like semiconductors. In case of intrinsic semiconductor, the charge density or density of charge carrier, holes and electron, it's equal, because you must be understanding why it is equal, how basically electron and hole are forming. Holes always conduct current through like valence band, or they are staying in valence band, and electrons in conduction band. So that is like how things work actually. But when we are adding some doping, in that situation this number density gets imbalanced. In case of n-type, the number density of electron or charge carrier will be higher, much higher compared to holes. In case of p-type semiconductor, the number density of holes will be very greater than compared to electron charge carrier. So these are all things like, and we saw in case of intrinsic semiconductor, it's Ne equal to Nh equal to Ni, and this we can easily write into Nh equal to Ni square. But in case of extrinsic semiconductor, it's definitely true that Ne is not equal to Nh, right? But still here also this relation hold, this is equal to Ni square, where Ne is the number density of electron, or electron number density of electron in whatever the like n-type, p-type semiconductor. Nh is number density of holes, and Ni is the number density of charge carrier in intrinsic semiconductor. Remember that. Then this relation still hold in case of p-type and n-type semiconductor. So we can see some small application just about like these same things, and then we will continue with the topic. And we saw actually that this density also depends on temperature, right? So here we saw that this relation, that Ni is equal to, it's a t raised to power 3 by 2 e raised to power minus eg divided by 2 kt. K is Boltzmann constant, T is temperature, and this is free energy, right? So this is the intrinsic charge carrier density. So this relation you try to remember, it's important. Okay, yes. So this is the relation where Eg is actually Fermi energy level. So remember these relations and let's see some simple application of the concept that we studied. And so here a silicon specimen is made into a p-type semiconductor. So you must be understanding how it is made p-type semiconductor. So silicon, it's made to p-type semiconductor, right? P-type semiconductor by doping on an average of one indium atom. So one indium atom in 10 raised to power 5 into 10 raised to power 5 silicon atom. This is the concentration, like how much doping, how much impurities is added, that is given one indium atom in these many number of silicon atoms. The number density of atoms in silicon specimen, so we can write actually number density of silicon atoms, that is given by 5 into 10 raised to power 28 atoms per centimeter per meter cube. So means like 1 meter cube of volume of silicon if we take, then it will have these many number of silicon atoms. Find the number of acceptor atoms, means like p-type, that indium atom in silicon per cubic centimeter, and this is per meter cube. Okay, so we understood. First thing is in 1 meter cube, it's these many number of atoms of silicon. So I can write number density of silicon in centimeter cube. In 1 centimeter cube, how much it will be? So like it's 5 into 10 raised to power 28 divided by, I can simply convert it into 10 raised to power 6 will be per centimeter cube, and this comes out to be 5 into 10 raised to power 22 per centimeter cube. Now I know actually in these many number of atom, like these many number of atom, there is one indium atom. So in these many, you can write in 5 into 10 raised to power 5 silicon, one indium atom. So I can write in 5 into 10 raised to power 22 silicon atom. Number of indium atom is 1 by 5 into 10 raised to power 5 multiplied by 5 into 10 raised to power 22, and that will comes out to be 5 10 raised to power 17 per centimeter cube. So this is the density of p-type, like you can say the impurity, p-type impurity, indium atom added, that density, number density should be equal to this. So I think like it's straightforward problem. You should not have problem in solving this type of questions. Okay, so let's talk about next case. A pure silicon at 300 Kelvin has equal electron and hole concentration. So means pure silicon means what? It's intrinsic semiconductor, and that means it's Ni equal to Ne equal to Nh, that is equal to 1.5 into 10 raised to power 16 per meter cube. This is the like number density of holes and electrons, and that is equal to intrinsic density, number density of intrinsic charge carrier. And here hole concentration of 1 points are like this, by doping by indium increases Nh to that. So now in this some doping is done by indium result in Nh equal to 3 into 10 raised to power 22. Clear? And now calculate Ne. So definitely when doping of indium is done, then Ne will reduce, and like because this is much larger, so number of hole electron concentration will be less. But we know that here the relation is simple. So this is your Nh, so you can write Nh multiplied by Ne is equal to Ni square. Everything is given straightforward. Nh, it's like 3 into 10 raised to power 22. Ne, it's asked to find Ni square, so it's basically equal to 1.5 into 10 raised to power 16 multiplied by 1.5 into 10 raised to power 16. Now I can solve easily, and E is coming out to be, this is 3, so this is 1.5 into 1.5 into 10 raised to power 32 divided by 10 power 22, so it's 10 raised to power 10, and 3, this is 0.5, and this is coming out to be 0.75 into 10 raised to power 10 per centimeter cube. So this is the not per centimeter, it's per meter cube. This is the number density of electron charge carrier in p-type semiconductor. So you can see it's like much smaller than this here indium atom or holes actually. So this you can easily 1575, yes, that's right. So calculation you can check it. So I hope like easily you can solve this type of problems. Okay, see next problem. The band gap energy in germanium delta Eg is given as 0.68 electron volt. Assuming that the number of whole electron pair is proportional to this, so means I can write the number of charge carrier will be like twice the number of holes or electron, is it? Or either you can write charge carrier will be Ne plus Nh, and that you can write 2 times of Ni. Clear? And proportional to, so I can write 2Ni is proportional to what, like e raised to power minus delta Eg divided by 2 kT, or if I'm writing this total as let's say Ni, number of charge carrier, this proportionality cancel, I can write some N naught, so then it's e raised to power minus delta Eg divided by 2 kT. Okay, so this I can write it this way. Now it's find the percentage increase in the number of charge carrier in pure germanium as temperature is increased from 300 to 320 Kelvin. So it's here you can see as we are increasing the temperature, these like N will increase. So you are asked to find the percentage increase. So here I can write let it's N1 at 300, that will be equal to N naught e raised to power minus delta Eg divided by 2k T1 at N1 at T1 temperature, and I can write N2 at T2, so that will be N naught e raised to power minus delta Eg divided by 2k T2. Then the percentage increase or change, I can write percentage increase in number of charge carrier, that will be equal to what, N2 minus N1 divided by N1 multiplied by 100. I can substitute everything. So this will be like, first thing is this can be rearranged as N2 by N1 minus 1 into 10 raised to power like into 100, and N2 by N1 it can be written, if I am substituting this simply like N0 and N0 gets in cancel, this will be like equal to, so it comes out to be e raised to power minus Eg divided by 2k T1 plus delta Eg divided by 2k T2 minus 1 into 100. This you can write actually, that is also equal to e raised to power delta Eg divided by 2k, and this is 1 by T2 minus 1 by T1, right, and minus 1 this into 10 raised to power 100. Now I can substitute the values actually, and in that case if I am taking it minus out, then it will be 1 by T1 minus 1 by T2. So here this value it's minus let me first, so delta Eg divided by 2k 1 by T1 minus 1 by T2, or here it's I have actually T2 minus T1. I can solve for that too also. Actually here there will be like N2 by N1, so N2 will be like it is T2 minus it will be T1, so it will be also here T1 minus T2. So then I am getting this, and like let me substitute it 0.68 electron volt to K comes out to be 2.82 into 10 raised to power minus 5 electron volt per Kelvin, and this is 1 by 300 minus 1 by 320 in Kelvin, and here I'm substituting directly the value of K, Boltzmann constant, in electron volt. The value of K in electron volt actually it's 8.62 into 10 raised to power minus 5 electron volt per Kelvin. So now solving this we get directly it comes out to be 0.8 0.82, and then if I'm substituting it here, then we are getting the percentage. It is e raised to power 0.82 minus 1 multiplied by 100, and this finally comes out to be 127 percentage. So the increase, as temperature is increased from 300 to 320 Kelvin, the increase in the percentage increase in the charge carrier will be by 127 percentage. So this is all about this problem. Okay, let's next talk about PN junction diode. It's like basic semiconductor device, very simple device, but very important actually. You will see ultimately from this device we make transistor and so on. Actually all things like are sort of like derived from this device, and it has like a lot of use. Try to understand, it's like easy, it's not complex. First let's understand what is a PN junction diode. So it is a semiconductor crystal in which on one side its acceptor impurities added. Acceptor impurities means p-type, and other side donor impurities added. Is called a PN junction diode, or we can call it simply a diode or PN junction. In simple term, you can understand it's like we understood p-type semiconductor, we understood n-type semiconductor. So if I am having one p-type semiconductor, another n-type semiconductor, like fixing, joining them, then that will be like, remember it, it's just a language to make you understand that what it is actually. So it is a like, this is a, I am having on one side it's p-type and another side it's n-type, and this is called your PN junction, simple term. But it's actually not formed by combining one p and n-type semiconductor. That is not, it's not like one p-type semiconductor we are taking, another n-type semiconductor, and like both are glued at the junction. That is not at all a PN junction, remember that. For understanding purpose, you can feed it just like that, is it? So how it is actually formed? It is a semiconductor crystal. On one side p-type impurities are added, diffused. On another side we are adding n-type impurities. So then finally we are having one p-type semiconductor crystal, n-type semiconductor crystal, and this cumulatively form a PN junction. Okay, so PN junction, like it's a basic semiconductor device where a semiconductor crystal in which one side it's acceptor impurities means p-type, and another side donor impurities are added, and finally we get, and that is called PN junction. So like what will happen actually here, if this is our p-type and this is n-type, right? So here what will happen, a hole concentration will be higher this way, and on this side it will be electron concentration, right? Some electron, one or two might be here also, and similarly some hole that will be like rarely. So this is, now initially just understand, let's try to understand it more like clearly. So try to understand, let's say this is the just, we have added the impurities, then what will happen, this will be the situation. But if we are letting it allow or to settle down, then do you think the situation of this junction will be just like this? Actually it will not be, right? Another important point is that you must be already clear that if I just look at it, n-type semiconductor, what is the net charge on this semiconductor, whether it's like positively charged or negatively charged? And the answer should be neutral. N-type semiconductor, it's also neutral. P-type semiconductor is also neutral. We studied that in the property of N-type and P-type semiconductor. So both are neutral actually. Now if we allow it to like settle for some time, then because of diffusion process, and diffusion process you must be knowing, whenever the concentration of something like is higher on one side, then it try to diffuse to the region where its concentration is less, right? So because of that, what will happen, you can see in this region, like here definitely there is also hole concentration higher, here electron concentration will be higher, but these can't diffuse this side, these holes can't diffuse this side. But here at this junction you can see there is possibility on this side, on right side it's electron concentration higher, on left side hole concentration is higher, and they have like reason to diffuse to this other side where the hole concentration is low, and this side electron concentration will high, electron concentration is also low. So what happened actually, after some time, like electron and holes diffuse at the junction towards other side, or you can say lower concentration side, right? So hole diffuse to N side and electron diffuse to like P side, and this will result in a situation actually. Try to understand it. So here finally we get something this like this condition. So here finally what will happen, now see, look at it, from this side holes will be diffusing this side, from N side electron will be diffusing P side. Originally this was neutral, originally this was neutral, but when hole will be diffusing, or additionally you can say electrons are coming this side, definitely you must be understanding here what will happen, electron concentration will increase, and on like negatively charged, on right side it will be positive charge accumulation will start. So actually here like we will have positive charge, and here negative charge will arise, and these are holes actually. Another thing is, in this region there is hole concentration more, in this region there are electrons, is it? So they have, this region have one side holes, another side electron. But if you look at it, this region actually these like major charge carrier, so this central region is depleted, means the major charge carrier are not available there, they are finished actually. So this is called depleted region, or this is called depletion region. Is it? Now another thing is, so if diffusion is taking place, then still the concentration on this side is higher. Try to understand it. We understood p-n junction, it is simply a like crystal semiconductor or semiconductor crystal in which on one side p-type semiconductors, p-type impurities are added, on another side n-type impurities are added, and that is termed as a p-n junction. Now I am trying to understand more about it. So what we did is, initially let's say we were having only intrinsic semiconductor, means pure semiconductor. Now we are trying to create a p-n junction. So on one side we added p-type, on another side we added n-type impurities. But like after some time, is it? So this is the situation immediately after adding the impurities. But if we are letting it cool, or you can say like settle things, then after some time the situation at this junction will not be just like this situation. So what will be the situation that I am trying to explain you? The situation will change to something like this. So here we have a third region basically, and this we call depletion region actually. So this is called depletion region. And here what is happening? So electron, because on this side and side here the concentration of electron is higher, so they will diffuse towards other side where concentration of electron is low. And similarly on this side, on p side, concentration of holes is higher, so it will diffuse to other lower concentration side, and that will result in this situation. If we look at it actually in this region, what about the charge actually? So it will not be, remember it, I am taking that effectively this side will have some negative charge, effectively this side will have some positive charge. The charge density will be something like this. On this side it will be like negatively, and this side it will be positive. So this is the charge density in depletion region actually. I have just drawn it a little bit bigger, so actually it will be only limited up to exactly that boundary. Okay, so this is the charge density in depletion region. Okay. All right, so now the point is that in this situation we got this charges positively charged and negatively charged, and holes we can treat them like positively charged and electrons negatively charged. So now what will happen actually, after some time these electrons, if they want to jump, like go diffuse this side, then they will experience some resistance because of this, because these negatively charged will try to oppose that. Similarly these holes, they want to move toward this side, then they will experience some repulsion resistance because of this positive boundary. So after some time the equilibrium will arise and there will be no further diffusion, or effectively I can say the diffusion of holes and electron will stop. Understanding? And finally we have this PN junction where we have in the center there is a depletion region. So let's talk about more like what we can say more about depletion region. Depletion region, first, what is depletion region? You must be clear with that term. So depletion region is a region, is it, in the middle of PN junction or at the center of PN junction, where you can say like there is no majority charge carrier. It's a region depleted of majority charge carrier, and its thickness, is it? So depletion region we understood. What about its thickness? Will it depend on something, or it will be like constant for any PN junction, or what we can say about it? So actually the thickness, we can understand it, it depends on the doping concentration. If p-type and n-type, it's like, let's say, highly doped. Understanding? In that situation what will happen, the density in this region will be high, and in this region p-type will be high, n-type. So they will diffuse this side and they will diffuse this side. So when like even from this region, small region, the diffusion, is it, electrons are diffusing from p-type. So here thickness of depletion region depends on the electron and hole concentration, or I can say doping. If it is, or you can write highly doped. What do you think for highly doped? Thickness should be higher or lower? Because highly doped, so maybe like you can say more diffusion will take place. No, but here, yes, you can say the diffusion will be more, but in highly doped, the thickness is less. Thickness of depletion region is, thickness is small. And here you can write lightly doped. In this thickness of depletion region, thickness will be high, right? So this is okay, we can understand why this happened actually, so that you can understood in this way. So when the concentration is very high actually, right, like this, on this side, and here holes. So now what is happening when this depletion or this flow or diffusion stops actually? These will diffuse this side. Here they have sufficient large number of holes. In a small region here has large number of electrons. They will diffuse to the other side, right? This way holes will arise. So here some positive charge will arise, and here negative charge. Because the concentration of holes here is high, concentration of electron here is high, so even like from small region there will be sufficient large number of electrons available here. Similarly, from even a small region large number of holes will be diffused this side, and these holes will produce high potential actually. So that, or you can say we define that potential barrier, right? I will tell you that. So they create sufficient barrier so that no further holes can't jump from like p side to n side. Similarly, they create sufficient barrier, potential barrier for electron also. No further electron can't jump from n side to p side. So that result in this thickness is small when it is highly doped, and when it is like lightly doped, more like there is probability, there is like more holes can diffuse from even from far away region. Even from far away region electron can diffuse this side. So that's way actually highly doped region thickness is small, lightly doped semiconductor then thickness will be high, right? This is about depletion region, its variation, thickness. And here you must be understanding that actually there is a potential difference arises in the depletion region, is it? So this you can say potential difference, if I am taking this is 0, then this will be something like positive. So here the potential difference will be something like this. So this potential difference we write potential barrier. It is the potential difference in the depletion region. The potential difference in the depletion region is termed as potential barrier. Barrier, you must be understanding why it is. Barrier means which creates some resistance, which try to oppose, is it like offering some resistance or some like problem to flow something. So these are creating actually barrier to flow holes and like barricade, is it some like fencing that is barricading actually. So similarly these like electron, they have negative potential is creating barricading or barrier for electrons movement from n side to p side. So this potential we call potential barrier. So the potential will be like, if I am taking here potential 0, then it will be like this way. So it will be barrier from his like for electrons. If they are jumping from n side to p side, they will be like, it will be also barrier for holes to jump from p side to n side. So this is your potential barrier. This potential barrier actually depends on the semiconductor. So it's like potential barrier it's 0.3 volt for germanium semiconductor or germanium p-n junction, and 0.7 volt for silicon p-n junction. So the value is almost fixed and it's equal to this, and the thickness of this is in something like micrometer. So the electric field in this region is actually quite large. The thickness of depletion region is of the order of 10 to like -6 meter, something like that. So you can write the electric field strength for silicon, it will be 0.7 divided by 10 to the power minus 6. It's basically 0.7 into 10 to the power 6. Is it? That will be like your electric field Newton per Coulomb. Understanding? So that much, like you can say in depletion agent the electric field strength is quite high, right? So I hope like we got simply this is called PN junction. Is it? Its symbol. So this PN junction notation is this. It's denoted this way. And here this arrow like pointed, this shows N side and this is P side. This is PN junction. This is also called PN junction or PN, simply called junction diode or diode. So this is the symbol of a PN junction diode. Now we understood potential barrier, that is 0.7 volts roughly for germanium like PN junction, and if it is made of silicon then it will be roughly something like around 0.7 volt. The thickness of depletion region depends on the like doping concentration, or like whether it's highly doped or lightly doped. So in case of highly doped, thickness of PN junction or depletion layer will be like very small. In case of lightly doped PN junction, thickness will be like quite large. Comparatively it will be large. Overall if we look at it, then it will be something of the order of 1 micrometer or 10 to the power minus 6 meter. If we go for some like electric field strength, then that will be like in of the order of 10 to the power 6 Newton per Coulomb. Okay, so now what happened actually, as I told, after some point of time there will like this region will be in like equilibrium. Understanding? So I said like almost like diffusion will stop. Is that like clear? Truly like diffusion? No further diffusion, it's like no at all. After that electrons are moving from N side to P side. What exactly is happening there? So still equilibrium means like you can say number crossing on both sides will remains constant. So basically still even in equilibrium situation, still holes and electrons keep on moving, and there are some mechanism, is it, and the ways. So based on that they constitute some current in equilibrium, and these currents we define one as drift current, another is diffusion current. Let me try to explain you what are those two terms exactly. Okay, so let's talk about diffusion current and drift current. So one is diffusion current, okay, I diffusion current. So what is that? Let me try to explain you. First thing is, yes, that is your like if I look at it overall, there is no current flowing in this transistor. If you like simply connect here, definitely like it's not even circuit is completed, so there will be no current in like overall. There is net current, is it? You can write here net current through diode is 0 in this situation, or you can write in equilibrium. There will be no net current. But what is diffusion current? So here what I told, after some time this potential barrier opposes the movement of electron from this side to that side, N side to P side. Similarly this potential barrier also opposes the movement of hole from P side to N side. But there are few holes on P side, few electrons on N side which have high kinetic energy, and they are able to cross even that barrier, and they able to jump this side hole and electron from N side to P side. And that way, so if holes are jumping from this side to that and electrons are jumping from here to there, is it high kinetic energy, what will result? The electron movement this side, so current will be this side, hole positive movement this side, current will be this side. So that will result in a current from P to N side, and that is called diffused current. right? So only those electron or holes having high kinetic energy are able to break the or cross the potential barrier and jumping to other side result in a net current from P to N side is called diffused current. So I hope you are clear. Normal situation, once the potential barrier is set up, electrons do not have sufficient energy, they are not able to cross the barrier, and similarly holes also. But few electrons and few holes have high kinetic energy and they are still able to cross that barrier, and electrons jump from n side to p side and holes jump from p side to n side, and overall result in a net current from p side to n side, and that current is termed as diffused current. Clear? So that is called as your diffused current. Another is called drift current. So let me tell you what is this. Is I drift. Okay, what is drift? So here, as I told, actually electric field in depletion region, how much? It's of the order of like 10 to power something 5 to 10 to power 6 Newton per meter per coulomb. You must be understanding that this field is quite large. So what happened actually in this situation, if due to thermal heating some electrons are like hole pairs are generated here, understanding? I mean, like, first thing is some electron getting high energy here, holes getting high energy here, they are jumping, crossing the barrier, resulting in that is termed diffused current. And here also, like, it's not that no further hole pairs are generating it every time. Hole pairs are generated, but what happen actually, if one new hole pair is generated, another hole like an electron combine and they finish basically. So that way overall, if I look at it equilibrium, the number of electron and hole pair remains same. But in this region, because there is a strong electric field, so what happened due to thermal heating, when some bonds are broken actually in this depletion region, and here you can see one electron hole pair will be generated. What will happen? The electron will be pulled this side because of field and hole will be pulled this side. Understanding? So just try to understand it. Here there is no electron hole pair, but when some one bond will break, one electron, one hole will be generated. Electron will be pulled this side and hole will be pulled this side. And now you can see electron pulled this side, hole pulled this side. So due to these, there will be net current on this side. And this is termed as drift currents, is it? So due to heating, new hole electron pairs are generated in depletion region, and because of high electric field in this region, holes attracted towards p side and electrons towards n side by electric field due to potential barrier. By electric field due to potential barrier result in a net current from n side to n to p side is called drift current. So that is defined as your drift current. Understanding? So in this situation, like now, how we can increase the drift current? So there are two possibilities. Either one is increase the temperature. If temperature is higher, in that situation also drift current will be increasing. And but if temperature is higher, drift current is increasing, electron and hole will also gain more energy. So simultaneously diffused current will also increase. So when there is no biasing. Now what is biasing? Biasing means when it's not connected to any battery, is it? So when no biasing, at that point of time, this is I diffused and I drift, both always remain equal, result in net I equal to 0. I diffused equal to I drift. Even we are increasing temperature, this will increase also. So at all temperature, when no biasing means no battery is connected, at that point of time diffuse and drift current both remains equal. And so I hope like you understand what is diffused current, what is drift current. But yes, you can say the magnitude of diffused current will increase, magnitude of drift current will also increase if temperature is increased. Clear? Another way to increase the diffused current or drift current is what? Is it? So drift current can be increased if we are increasing the potential or the field between these, then also it sometimes result in increase, is it? Or another way, when we are connecting a battery, pushing these holes this side and electron this side, then also your diffuse current can be increased, right? So this is just basic things about a p-n junction. Let's talk about now how it behave, what happen when a battery is connected across the p-n junction, and we call that biasing of p-n junction, biasing of diode. It can be done in two ways, and we define as one forward bias and another one is reverse bias. So let me talk about both of them. Okay, next is biasing of a p-n junction. Biasing means simply connecting it to a battery or external battery or a potential difference. That is simply termed as biasing of a p-n junction. Now it can be done in two ways. So biasing, one we define is forward biasing. What it mean? So here we have like p-n junction. This is a p-n junction, depletion region. This is p side, n side. So when p, we normally call it something like similar to positive, n means negative. It's actually n means n type, p means p type. So if it is connected in this manner, when like here potential p is connected to positive terminal and is connected to negative terminal of a battery, this way this biasing is called forward biasing. You must understand actually here it mean if I am like saying drawing it a p-n junction like this is also our p-n junction. This is also forward bias. Another possibility can be like here I am marking this is terminal A and this is terminal B. The point is the potential of terminal A must be higher than potential of terminal B, then it will be always in forward biasing. If VA is greater than VB, it will be forward bias. Like, see the cases. If I say VA is 0, like 5 volt, 0 volt, biasing. What about forward bias? Yes, it is forward bias. Clear? Correct. If it is, let's say, 0 and it's like minus 5 volt, then also it's higher than this. This is also forward biased. If it is 10 volt, it is 5 volt. Still you can see A is at high voltage, high potential. This is also forward bias. If it is, let's say, minus 5 volt and it's minus 10 volt. In this situation also you can see A is at higher potential compared to B. This is also the condition of forward bias. So even when potential of both the points is negative, but still because potential of this point is higher than potential of this point, then also this will be the condition of forward bias. So in all such cases it is the forward biased, right? So forward bias means P is connected to high potential compared to N side. That is the condition of forward bias. Simplest case is simply connecting a positive terminal of battery to P type semiconductor, negative terminal of battery to N type semiconductor, and that is called a forward bias, right? Now let's see what happened actually, like in case of forward biasing. So in case of forward biasing, this is a forward bias condition. This is depletion region here, and negative, 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 positive, positive, and potential barrier. And this is positive, negative, P, and now what will happen? You see here, P positive, and holes we treat them like positively charged. Electrons. So now you can see here actually holes are feeling resistance to jump this side, but this will try to push them further. So it will push the holes further. Electrons again feeling resistance to jump this side. This negative will push these electrons this side. So this way you can see they are helping in jumping, in crossing this barrier. So what happened actually in this situation in case of forward biasing is it, if this is a potential barrier, we write it VB, that is also called barrier voltage. If it is V, so it's like no biasing condition. Then what can happen in case of forward biasing? It reduces actually effectively because it like opposes, understanding. So in this situation holes will be pushed further this side and electron will be pushed this side. So overall you can see there will be net current, and here you can write the diffused current actually increases and drift current reduces actually. So here you can understand this way also, I diffused and this is I drift. So drift current reduces very small, overall diffuse current increases. So in this way you can see actually what will happen, current will flow in the circuit through the PN junction, understanding. And this can be done all experimentally by connecting in this manner. So I hope you understood the meaning of forward biasing, what can be the different possibilities for a PN junction to be connected or to be a forward bias. So let's just consider this situation, a circuit diagram for it, this, and here in case of forward biasing we connect one milliammeter. So milliammeter is connected here, and one battery is connected, voltmeter, this and this, rheostat, and forward biasing. So it will be like positively charged, it will be negative, positive, negative, rheostat, and this is positive, negative, positive, negative, and here this is PN junction, P and current. So it milliammeter will be measuring, and here by this moving it right left we can change the potential drop across this, is it? Now if we plot its graph actually, so what will happen when the potential drop this V is less than this barrier potential? In this situation what will happen? Can you just imagine, almost there will be no current, because diffuse current will be almost equal to drift current up to that time, is it? So up to this potential drop is equal to this potential barrier, there will be no current. So if I plot its IV graph for forward bias, it's important, try to remember it's, this is a I versus V graph. I is in milliampere, V is in volt. Okay, so then what happened? Up to certain point there is no current, because till this potential is not more than this potential barrier, no current will flow. After that some current starts slowly flowing like this, and then after some time it increases rapidly. So this is your IV characteristic of, this is called your knee voltage. After this voltage, current increases rapidly with increasing voltage. Knee voltage is actually equal to your breakdown potential barrier, that is 0.7 volt something roughly for silicon. That also depend on the doping concentration also, and roughly it's 0.3 volt for germanium. So this is your forward bias characteristic we call for a PN junction. Now you can see after certain time the current in this increases rapidly. So here the resistance, is it? First thing is, here you can see the graph is not a straight line, so it will not have a constant resistance. Here we calculate dynamic resistance, is it? So it offer a resistance of something like 10 to 25 ohm in forward biasing, roughly something like that much. Current increases after breakdown voltage, not breakdown, potential barrier, when V greater than V barrier voltage, then current in the forward bias will increase rapidly or more faster, is it? Here we calculate one dynamic resistance actually. Because you can see here this graph is not a straight line, so we calculate actually at different point. We can consider these 2 points and we will calculate delta I and delta V. So that's dynamic, we define here R dynamic, this is delta V upon delta I, that is called your dynamic resistance. So for forward bias characteristic we calculate dynamic resistance. For two nearby point you will be provided current and voltage values, and from that you can calculate the dynamic resistance. The resistance is in this range, and in forward biasing when the voltage applied potential difference is less than the potential barrier, no current will be there. Once it is increases beyond that, then current will start flowing. And the resistance offered in forward biasing, it's like quite small, it's not very large. We will see actually in case of reverse biasing the current is very high. So here you can see this barrier is only offering some resistance, otherwise it's like in forward biasing supporting majority charge carrier, they are moving this side, they are moving this side, further like continuously holes will be supplied from this side, electron. So we will have like large current flowing in this circuit, and that large current will be only in some milliampere. It's not like 10 ampere and 5 ampere something like that, no, it will be milliampere. So this is the condition of a forward biasing. Let me talk about reverse biasing also. Okay, so reverse biasing is just exactly opposite of forward biasing. This is N side, this is P side, P and junction. So when N side is connected to high potential, or you can say N side is connected to positive terminal of battery, P side is connected to negative terminal of battery, the PN junction is said to be for reverse bias. So when N side is connected to high voltage and P side low voltage, it is called reverse biased. Right, again here also there can be different possibilities. So one way is like this, just consider it. I'm taking its A point, this is terminal B. So in all like situations VA, VB, only the condition is that VB must be always higher, is it? So here if I'm writing this is, let's say 0, this is 5 volt, you can also write here in this situation biasing, reverse biased. This is minus 5 volt, 0 volt, also reverse biased. This is minus 10 volt, minus 5 volt, reverse bias. 10 volt, is it? It must be at 15 volt, or I can write 5 volt and this is at 10 volt, also reverse bias. So all these situations are like conditions belongs to reverse biasing of a PN junction. So in reverse biasing, what happen actually, if we look at it like in detail, so in this situation negative connected here, positive connected here, already there was barrier, these potential barrier was not allowing electron to jump this side. Now you see this positive will try to even pull these electrons further away, is it? It will be pulling these electrons this side, it will be pulling holes this side. So it will try to even stop the current whatever it was flowing that side earlier. And you can see this negative, it will be like supporting this negative potential, positive will be supporting this potential. So in this, in case of this is the condition of no biasing, then in case of reverse biasing the potential barrier increases. And so because of that you can definitely say the drift current will, what will happen, it will reduce drift current, but diffuse current, because here you can see the electric field in this region will increase, right? Potential barrier is increasing. This is VB in reverse biasing, potential barrier. Drift current, diffuse current will decrease, but drift current will increase. So in this situation you can say the current in this circuit will be like negligible and very small, is it? It's in something like micrometer. So first let me draw a diagram to test it actually, like for different values of potential drop. So again the circuit diagram will be just similar to what I draw for forward biasing, only the here potential, the terminal will be connected in opposite sense. So this is your PN junction. Again here we will connect one microammeter because the current here will be like very less, and this is a positive negative reverse biasing battery, and it's connected here this rheostat and battery reverse biased. This is connected positive negative rheostat, and this is voltmeter and microammeter, and this is your PN junction, right? So here again what happened actually, we are moving it and we are changing this, right? So and if we plot this graph actually for here like reverse biased things, this is I in microampere, this is voltage. Here the current initially, like, because you can see it's even offering more resistance, it's not even allowing the electron at all, but whatever the electrons will be like new, like electron pair will form, like hole pair formed here, they will be immediately pulled. So because of that drift current increases by very small amount and diffused current almost reduces. So overall there will be small current flowing in this direction, understanding? So in opposite direction, opposite in the sense like earlier it was flowing this side, now it will be this side, current will be flowing. So here the current is very small, something like that. And if we increase this voltage still too much, like increasing further, increasing, then there comes one position, one condition, after that the current increases drastically, and this is called V breakdown. This is called breakdown voltage. Means sort of like here you can say this PN junction failed actually. When here in this situation, when potential drop across this in opposite direction is becoming very high, immediately drastically a large current flow in opposite direction. This you can see a large current flowing, and this potential at which this situation, this condition happen, large current start flowing in this PN junction in reverse direction, we call this breakdown voltage. Up to here you can see that it's like very small current, so you can say it offer a large resistance in reverse biasing. It's actually of the order of 10 to the power 5 ohm, 5 or 6 ohm, something like that. Current you can say definitely very small, is very small, only few micro, and in reverse biasing you can say here drift current increases slightly, diffuse current reduces. So that is the situation, and it almost you can say does not allow the current to flow in opposite direction because of high resistance. Definitely P terminal is connected to lower potential and terminal is connected to higher potential, and this is the condition of reverse biasing of a PN. So what about like depletion layers? Here you can see in the case of like these will be like pulling these holes this side, electron this side. So here we can say depletion layer, width of depletion layer increases, width of depletion layer increases in case of reverse biasing, and the breakdown voltage it's 25 volt is something for GE and 35 volt for silicon. So these are roughly breakdown voltage for germanium and silicon, and this is your biasing of PN junction. I hope you understood what is like a PN junction, like how current, biasing, depletion layer, diffused current, drift current, and biasing, forward biasing, reverse biasing. In case of forward biasing, it offer very small resistance. In case of reverse biasing, it offering large resistance. And you must be also understanding why this is happening, means why in case of forward biasing the resistance is low, in case of reverse biasing resistance is quite high, very high I would say. So this is all about PN junction. Let's continue from here onward in the next class. Thank you so much.